Well, good evening. Welcome to SpaceOddities. Thank you for joining us on this Tuesday evening. Hope everybody's well and enjoying the incredibly good weather you seem to be having in the UK at the moment. You still got good weather in the UK?
Yeah, not bad.
Well, we got thunder and lightning and torrential downpours at the moment.
Yeah.
Oh.
We had a heavy rain storm last night.
Oh, right. But,
Yeah.
Well, I'm just praying that it's okay when I come on a visit to London in June. So let's hope the good weather persists. Anyway, enough of that old chutney. Joined this evening by Michael and Roger and Daz and Lou. How are you all, gentlemen? Everybody okay?
Thank
we're
you.
lovely, thank you.
All good.
All good. Yeah,
Yes.
Great, fantastic. Well, on the show tonight, we're going to carry on with the theme that we were talking about last week, if you were with us last week, and that is the theme of galaxies. But this week we're going to look at it from more of a cosmological viewpoint. We're going to be looking at the latest discoveries by the James Webb Space Telescope and asking the question, what the hell is going on? And do cosmologists have to start rewriting the textbooks, as it were, in the light of the Webb discovery? And also, Lou's going to be telling us about another big problem with cosmology at the moment, namely the Hubble tension, which
It's
is
the same thing. It's what the hell is going on?
Yeah, it's
That's our show today.
Yeah. So we can't give you all the answers, let alone fix them, of course. But we'll tell you where we are at with these particular problems. So there we are. We've also, of course, got our regular features. We've got our weekly delve into the insanities of social media with Einstein of the Week. We've got, obviously, Roger's Night Sky and Gallery. And we've also got the Constellation of the Week, which this week will be delivered to you by Michael.
Yay.
So we've got quite a packed show coming up. Something that I was just reading about actually a little while ago, Lou, which you may want to talk about, the remarkable reprogramming of Voyager to reactivate its thrusters after 20 years. Do you want to talk a little bit about that?
Well, only in general. This spacecraft, this little bundle of joy, has outperformed any of the wildest expectations that we had for it. You might remember that when it was launched, it wasn't called Voyager. It was called MJS, Mariner class, Jupiter Saturn. Well, so there is an engineering model. This was built before we had digital twins, right, where we tried to replicate the functions and activity of a spacecraft digitally. So there's an actual model of it at JPL, and you can use this to diagnose problems on the spacecraft that's far out there. And the ground crews are just amazing people. They are gods. They perform the impossible, just like most of NASA, every day on a shoestring budget. So I don't have a lot of specifics, but it's just an incredible feat.
Well, the problem with the thrusters on Voyager is that after a while, the fuel lines get clogged with residue and they lose their efficiency.
You're talking about the hydrazine.
Yes, exactly. So they have a set of backup thrusters. These have not been activated in 20 years. So they thought they would try and reactivate the thrusters, because the efficiency of the primary thrusters was decaying quite alarmingly. Of course, they had to understand the code that was written back then, in a language that very few people are still familiar with, of course. And they managed to send a command to the spacecraft, and Voyager just turned around and says, "Oh, you want me to reactivate the secondary thrusters? Okay, no problem." And the thrusters came on again and performed perfectly after not being used for 20 years. Absolutely amazing, inspiring story, as all Voyager stories are inspiring. So there we are. Just one thing before we move on to the news.
This is what they're going.
All right, go on.
I guess I can't see it if I turn my camera off. Let's see here. How do I turn my camera off? Video background, none. Here we go. This is the kind of stuff they're going through. They're all paper documents. A lot. This is the for the IRIS instrument on Voyager 1982. The user's manual, so to speak.
Yeah.
And you go through this thing, and you get pages like this forever and ever. And this is what they have to go through. And where is each bit? Where is each byte? Where is each word in the file? I mean, it's remarkable. You have to be crazy to do this work, but they do.
They do. Yes. And of course, as time goes on, the sort of the expertise base is dwindling and dwindling. So
that's one way to put it.
Yeah, absolutely. Okay, so next week is the 3rd anniversary of SpaceOddities, and we are very happy to still be around after 3 years. We didn't know where we were going to be in 3 years and what we were doing. But we're very happy that SpaceOddities has lasted 3 years with your support, viewers, for which we are eternally grateful. We could not have been here after 3 years without you. So we owe you a big thank you. As for what we'll be doing to celebrate our 3 years next week, well, we haven't made any firm plans yet, but we will be having a competition, if you like, in connection with the viewers gallery. But we'll tell you more about that a bit later when Roger does the gallery. And so if there's anything that you would like to see us do to celebrate our 3rd anniversary, then pop it in the chat. Simple as that. If you have any ideas, we're mulling a few ideas over at the moment, but we think we should commemorate 3 years, and there we are. So without more ado, let's move on. We're going to go first of all to this week's news. So let me just set this up. And we will see what is in the news this week. Okay, hope everybody can see that. Just a few items this week. Look at this, seen over Colorado during an aurora. Ooh. Guys, what do you think this is?
Oh,
searchlight?
No.
I think some people thought it was Steve.
Yes,
Steve.
Yeah, but it wasn't Steve. Do you know what it turned out to be? It's the 3rd stage of a Chinese rocket dumping fuel.
Oh.
Yeah, it had been launched from China just a bit before that. And as it went over, well, not just Colorado, but quite a lot of the southwestern US, it decided to dump some fuel. But if you saw that in the sky, that's quite impressive, isn't it? It's like
So
like
just a comet tail.
Yeah, it's like a hyperspeed comet, isn't it?
Yeah, that's just the tail then.
Yeah, absolutely. So there we are. Chinese rocket dumps fuel over the southwestern US. I thought it was quite a lovely image. So I just thought I'd show you that. Okay, moving on. Tomorrow, there's going to be a flyby of an asteroid the size of a house close to the Earth. This is designated 2025 KF, and it's going to pass within 72,000 miles of the Earth. Now, that sounds quite a long distance, but in astronomical terms, that is a really, really close shave, because obviously the Earth, had it been a bit further on or a bit backwards in its orbit at the time, could have well copped that particular asteroid. And it is the size of a house. Not much more is known about it at the moment. Astronomers hope to get some more data tomorrow, but there we are. But it's going to pass, in terms of relation to the Earth, it's going to pass over the South Pole. So quite a near miss in asteroid terms. And if a house-sized object had hit the Earth, you can imagine it would have caused a total catastrophe. If it had, well, not just landed on land, if it had gone in the sea, it might have caused a tsunami.
Are the penguins in danger?
The penguins are fine. Well, they've all left anyway, Lou. They're all hanging out in the atmosphere of Venus. So
Creating phosgene.
Yes.
But I see it's another obscure measuring thing, though. I mean, houses vary. Is it a big house? Is it a bungalow? Is it, what is it? So
yeah. Well, if it were my house, of course, it would be the size of a small town. So
yeah.
Did they say so long and thanks for all the fish?
They didn't. No. Because believe it or not, penguins can't talk, Michael.
That's true.
Yeah, so there we are. Anyway, close call from an asteroid tomorrow. Nothing to worry about. Don't let the media tell you otherwise.
Actually, Andy, you say they don't talk, or is it they choose not to?
Could be. Okay, moving on. Very sad to report the death this week of the famous Indian astrophysicist giant Nalakar, and apologies to Indian viewers if I'm mispronouncing the name. He was quite a famous astrophysicist in India. He's passed away at the age of 87. I just want to run through his achievements because they're quite impressive. So first of all, he was a huge collaborator with Fred Hoyle, and they came up with the Hoyle-Nalika theory of gravity, an alternative to the Big Bang model. It's a steady state model, needless to say, integrating Mach's principle with general relativity, proposing a steady state universe where matter is continuously created, maintaining a constant density despite cosmic expansion. Well, we now know, of course, that the steady state theory was wrong, but apparently Mr. Nalika held on to that idea for all his life. But unfortunately, he's no longer with us. He founded the Inter-University Center for Astronomy and Astrophysics, recognizing the need for a centralized institution to promote astrophysics research in India. He established the University Center in Pune in 1988. Under his leadership as the founding director, it became a premier center for astronomy and astrophysics, fostering collaboration among Indian universities. And he was an advocacy for science communication. He wrote many popular science books. He was chairperson for the National Council of Education, Research and Training, Science Textbook Development Committee. He won the UNESCO Kalinga Prize for the popularization of science, and he received several prestigious awards from India, including the Padma Bhushan, sorry again if I'm not pronouncing that correctly, in 1965, and another one in 2004. And they are among India's highest civilian honors. So rest in peace, Mr. Nalika, and I'm sure you will be greatly missed. SpaceX are launching Starship soon, and they've now come up with a new date for the launch of IFT-9, Integrated Flight Test 9, of May the 27th. However, some question marks do remain over that because they haven't yet received clearance from the FAA, because they only submitted the investigation about the Flight 8 explosion on May the 14th, which hasn't given the FAA much time to analyze it and clear Flight 9 for flight, but they're optimistic that they will be able to do so. The launch window runs from the 27th to the 31st, so they've got a few days in hand. Talking of SpaceX, this week they launched their 475th Falcon 9 launch and put the 1000th Starlink satellite into orbit. Although it must be said that around 2,000 of those Starlink satellites have deorbited and are no longer orbiting, obviously. Then we move on to Australia with Eris-1. Now, if you're watching the channel, you know that we tried twice to cover the launch of Eris-1. The first time there was a fault in groundside equipment, which called the launch off. The second time, which we were very excited about, and thank you for joining us for that if you did, the front fell off. Basically, what happened was that there was an electrical fault, and both halves of the fairing, that's the nose cone at the top of the rocket, both halves of it just fell to the ground. And they are now having to re-equip it with new fairings, which could take a couple of weeks, they say, which was disappointing because this was Australia's first attempt at an orbital launch in 50 years. So this is why we wanted to cover it, because it was quite a big event. If it had been successful, Australia would have been in orbit for the first time in 50 years. The rocket did have a payload. It had a jar of Vegemite as the payload for this mission, quite predictably. But Gilmour Space hope to be back launching Eris-1 in a couple of weeks. And of course, we will cover that live if we possibly can.
Yeah, both the payload and the rocket have suffered no damage. So
that's right. The jar of Vegemite was intact after the accident.
Yeah, which is all good.
Yeah, so the fairing actually fell off the night before launch. So when we went to cover it,
and also just before we moved slightly down, you were talking about the Starship. Do I understand that this time they're forgoing catching the booster and they're going to splash down in the Gulf of Mexico?
Yes, they are. Then this will be the first time they've reused the Super Heavy booster. So they've decided not to try catching it as well, because it's being reused. So the Super Heavy booster will be splashing down in the Gulf of Mexico, and Starship, if it completes its flight, will be splashing down in the Indian Ocean. So there we are. We will, of course, bring you live coverage. On the 27th, it occurs at midnight UK time, if they make the 27th. But we will obviously put the live stream up on the channel, viewers. So keep an eye on the channel. You can see when it's happening. Another mishap this week as well. India lost a satellite. The PSLV-C60 rocket failed. It was going to launch an Earth observation satellite. Everything went well up until the separation of the third stage of the rocket, because it's a 3-stage rocket, which is normally very reliable. It's got a very good track record, this particular rocket. But after separation, the pressure in the combustion chamber dropped and it couldn't maneuver and couldn't provide enough thrust, and the satellite was lost. So commiserations, India. I'm sure you'll get up again very soon and get it right. These things happen because, what do we say? Space is hard. It's as simple as that. It doesn't always go to plan. So there you are. So that's just the news for this week. And a bit of a quiet news week again. But anyway, I hope you enjoyed that. What we're going to do now is to go straight on, I think, to Roger. If Roger is ready, willing, and able to deliver his guide to the night sky, and of course, not forgetting the all-important viewers gallery. So let's just put this up on the screen for you, Roger. There you go.
Oh, thank you very much.
That's my pleasure.
Right. Okay, so we're coming towards the end of May now already.
It's unbelievable.
Getting to the halfway point of the year already. So, yeah, we're getting through the phases of the moon. We're currently at the last quarter up through to the new moon next Monday. So, all well and good for that. And at the night sky, we're almost planetless, although we do have Mars still available to see, small as it is at the moment. But we are now gathering a pace with the summer constellations coming up now, with Vega, Altair, and Deneb for the summer triangle. And also that means we've also got the Milky Way starting to come out through, with Antares there down in the bottom of Scorpius. So all well and good there. And this is as from 10 o'clock. So the Milky Way core will not probably be visible until about 3 o'clock in the morning. But we will get there. But the majority of the planets will be coming up just before sunrise. We've got Saturn, Neptune, Venus, Mercury, and Uranus. Although the likelihood of you seeing all those is pretty pretty much impossible with the closeness of some of the planets to the bright dawn sky. But Venus will be visible, although it is quite low in the eastern horizon. So it will be a quite nice opportunity to see that. And as we progress through, we do get some interesting photo ops. Right, so we do have a interesting gallery with our regular contributors. First one is from Michael. This is the sun from a week ago. And this was taken with his Coronado and 178 ZWO camera.
Oh,
And
wow.
got some nice
Yeah.
filaments and proms on there as well. Lovely. Very good.
Oh, sorry. What date did he say? What date this was taken, Rog?
This was the 13th. It was just a bit too late to go into last week's gallery.
Right, because if you look at the 12 o'clock position, you can see a fairly longish
Yeah.
filament that
Mm.
actually lifted off, and it was measured at something like 93,000 miles long. It literally almost came down to the equator. It was absolutely massive. I mean, I have got a video from the first to yesterday, which I might play later on, but you will see that now we've gone sort of like past active regions. We've still got quite a few, but not as many as have in the past, to these massive filaments now, which are all lifting off, which are creating massive CMEs, but also massive coronal holes, and they are really huge. I might pop something up a bit later on if we get time. But yeah, it's absolutely fantastic. Lovely image.
Yes, very good. And then we have Lee with a beautiful image of the Great Rift area of the Milky Way, which he had in his local area. And this was 13 2.5-minute exposures. And he says you can even see the North American nebula. It's America Nebula, Lee, not American. Get confused on there.
It's like the Gulf of America.
Yeah, I was just thinking that.
Yeah.
They're claiming
And
everything.
this was his image.
Oh,
That's beautiful.
It's the North Mexico Nebula. Get it?
Yes.
Wow.
That's lovely,
Yeah.
Lee.
Mhm.
Look at that. That's
gorgeous.
Is that the North American nebula just to the third of the left?
yeah.
Yes,
In
yes.
Yeah.
It's the pink color.
The pink bit. Yeah.
Yes.
Yeah. That's good.
How pretty.
Lovely image, Lee. The
Lovely.
contrast in that is really good, isn't it?
Yeah.
He's done that well. I think it's because of all the frames that he's put together to get that. He's managed to get that just right.
That's
Well
stunning.
done, Lee.
Well done, Lee. Yeah, that's beautiful.
And we've got a couple from Kenneth. Some more 2-meter telescope images with the this one from Halakea in Hawaii, M65.
Oh.
Oh, that's nice.
And these are just 90-second exposures through the red, green, and the blue.
So that his 2-meter scope is on Haleakala?
Yep. This is part of the Liverpool telescopes availability, because they've also got a telescope down in Sliding Springs in Australia as well.
Haven't they got
So
evidence as well?
get some rather interesting pictures of the southern hemisphere.
Gorgeous.
Lovely.
Very good.
Beautiful.
And then he's got one of the Little Pinwheel Galaxy, NGC 3184. And this one's just under 40 light years away.
Wow, look at
Lovely.
that.
Mm.
That's amazing.
Yep.
Beautiful color.
Yeah, very
That's
nice.
incredible. Yeah. Wow. Well done. Fantastic, Kenneth.
Well done.
Another
Yep.
winner.
Yep.
Yep. And I've put in a few solar images this week. This is on the 14th and the 16th, just to give you some ideas of some of the activity that we've been getting.
Wow, look at that.
Those prominences are absolutely huge, aren't they?
Yeah.
There's one thing I did
you
know.
get some lovely arched animations from this if you could
Exactly,
do it.
but also because what you got to remember, this isn't a 2D object; it's 3-dimensional. So when you look towards the north, and like I said, I was talking about these filaments, that they are so big that you're actually being able to see a vertical profile to them as well. So they don't just look like a line. You can actually see that the actual stuff that where it's connected and things like that. So you've actually got a vertical profile, so you can see it is 3-dimensional. It's absolutely phasing.
Yeah.
I mean, the sun's very, very active for the period we're at, because I mean we are in the declining now. So we'll talk about that later.
Yeah. By the way,
I mean, there are an awful lot of sunspots, but the filaments and the prominences are going doolally.
Yeah, I mean, some of the sunspots that are there are really huge, aren't they, Rog?
Yeah, absolutely phenomenal size. Right. Well, here's my take on the North America Nebula. This is a slightly different process into what I normally do, because I've managed to get some details in the central area.
That's
all the different
nice,
brightnesses and
that's lovely.
Must have taken you all day to color that in. That's beautiful.
yeah. I didn't go over the lines or anything, so it was quite good for me.
Say, did you start with the corners and then do the edges?
Work my way in.
That's really nice.
By the way, Kenneth says about his image, he's currently redoing it using more functions in Pi. So if you want to
that's Pitt's insight.
yeah. I thought it was doing it with circles, but there we are. If you want to send in another image, Kenneth, of it, then please do. Obviously.
Yeah, I'll put them in.
We'll have to see the evolution of imaging.
Right, and the final one is an image from today.
Oh, look at that.
That's
very interesting. Interesting formation.
Angry, the angry sun.
Very angry.
Yeah, beautiful.
One of the few sunspots that we've got to see at the moment.
Yeah.
Although there are some more coming back round again, so it won't be long again. Won't be long. Right. So there we are, guys.
Great. Thank you so much, Roger. So there we are. Another gallery. Don't forget, if you would like to send in your images to the gallery, attach them to an email and mail them to gallery@spaceoddities.space. And thank you very much indeed. If you could just do one image per email, please, to make it easier to sort out this end, then that would be gratefully appreciated. In connection with this, next week for our 3rd anniversary, what we're going to do is we're going to take the top 10 images that have been viewed on the Space Oddities website, because don't forget, everybody who does submit their images has their own gallery on the website. We're going to take the top 10 most viewed images on the website from the gallery and get you, the viewers, to vote on your favorite. And the winning photographer, the person who took the winning shot, is going to receive a free Space Oddities t-shirt as a prize. So we're going to do that next week. So we hope you will be along to vote for your favorite image in the gallery next week. Okay, fantastic. Well, let's move on. We're going to, as I said earlier, we're going to discuss what is going on with cosmology at the moment, because there have been all sorts of headlines in the media, cosmology in crisis and, such. Is cosmology in crisis because of what the James Webb Space Telescope has discovered? And if it is, what could be the fixes for the problems with our current model of the early universe in order to understand exactly what was going on? And a little later, Lou is going to look at the other side of the coin and look at another cosmological problem, which is the Hubble, the so-called Hubble tension. So let's have a look at, first of all, the James Webb. Just let me sort this out. Okay, so the James Webb Space Telescope is challenging our understanding of our cosmic origins. It's challenging what we thought we knew about the very early universe. That is to say, perhaps the first billion years or so after the Big Bang, because what we thought we knew doesn't seem to be borne out by the observations of the James Webb Space Telescope. Now, let's not forget that the James Webb Space Telescope was launched specifically to examine, observe, and give us data from the early universe. And that is its job. That's what it was built for. So it's hardly surprising if what it is showing us doesn't agree with the data that we had before then, because obviously with astronomy, when you have new technology, we always learn something new, and quite often it doesn't agree with what we thought we knew, but that's how science works. So let's first of all have a look at an introduction to this. So the James Webb has given us completely unprecedented views into the early universe. It has gone much further back in time than the Hubble Space Telescope was capable of doing. Its observations are forcing the reevaluation of galaxy and star formation models. It's refining cosmological theories with fresh infrared data. Now, the standard model that we had up until the James Webb Space Telescope looks something like this. So first of all, about 13.8 billion years ago, the Big Bang initiated the expansion of the universe. And after that, we had a very, very, very brief period known as the inflationary epoch, where the universe expanded exponentially. And I worked this out. It expanded something along the lines of, if I remember the figure right, 15 million times the speed of light. Now, if you're going to say, oh, well, nothing can travel faster than light, nothing in the universe can travel faster than light, but there's no such limit on the universe itself expanding that fast. So this took place between 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, an unbelievably small period of time during which the universe expanded. And the analogy would be, it would be like taking an atom and expanding it to the size of a basketball in that tiny, tiny time scale. So after that, after the cosmic inflation, which it started for reasons we don't know, and it stopped for reasons we don't know, but all the evidence points to the fact that it did, because if it didn't, we've got lots of questions. And the inflationary epoch, first put forward by the astrophysicist Alan Guth back in the 70s, it answers lots of questions and seems to fit all the models. After that, we had what's called the era of recombination. This is when the first atoms formed, which led to the cosmic microwave background, this wave of radiation that travels across the universe. That is, if you like, the first light released by the universe. Before 380,000 years after the Big Bang, the universe was simply too hot and too dense for light to travel across it. But this suddenly cleared. It was being called the cosmic dawn, and we detect that that microwave radiation today. Since the beginning of the universe, it's been shifted towards the long end of the spectrum to microwave radiation, and that's what we see today. And that cosmic microwave background contains, we believe, the first seeds of the first galaxies, represented by very, very tiny differences in temperature in that radiation of perhaps the millionth of a degree, but that can be and has been measured. So after that, these density fluctuations created the first stars and the first galaxies. The JWST was specifically set up as an infrared telescope. It's able to penetrate dust because it is an infrared telescope. It allows us to see things that are otherwise hidden by dust. And it reveals high redshift objects. In other words, objects towards the edge of the observable universe that are moving incredibly fast. The key instruments are NIRCam, NIRSpec, MIRI, FGS, and NIRIS. Don't worry too much about these, but these are infrared cameras and spectrometers at different near-infrared and mid-infrared wavelengths. And its goal was indeed to observe the first stars and galaxies, what's called the cosmic dawn. Now, one of the things it's discovered is these massive galaxies very early on in the universe's history that were not thought possible to have existed that early on in the history of the cosmos. They are known as the red monster galaxies, and you can see 3 examples of them here. They are mostly sort of formless blobs. They don't have any structure. It was certainly too early for them to form spirals in the case of, spiral galaxies. And what do we know about these? Well, each one of those has a mass of around 100 billion solar masses. So these are getting on for the mass of the Milky Way, and indeed the size of our Milky Way galaxy. And they were formed 12.8 billion years ago. So about 1 billion years after the Big Bang, you had these red monster galaxies. So they obviously formed incredibly quickly. They were very efficient at star formation, converting perhaps 80% of the gas in those galaxies into stars. And when we talk about efficiency, we're basically talking about how much gas in the galaxy as a percentage of the whole is converted into stars. And this completely contradicts what our expectations of early star formation were. We didn't think that the early galaxies would be that efficient at forming stars. So there's obviously something we're not understanding there. And then the discovery of the most distant galaxy, JWST 14.0, and this is that. And you can see in the James Webb image here, it's a tiny, tiny little blob. That's the only way you can describe it in that vast array of galaxies as shown by the James Webb. It was, as we're seeing it, 300 million years after the Big Bang. Very, very early. Well, I know 300 million years is an incomprehensible timescale for humans, of course, but in the history of the universe, it's a very short period indeed. And it has a redshift of about 14, and that basically tells you how far away it is. It shows rapid star formation, but more to the point, it's enriched with heavier elements than we thought could have been forged by stars at that time. So it was producing these heavy elements as a result of supernova explosions much, much earlier than we thought was possible. And this extends the distance record and shifts the formation of the first galaxies backwards, because if we had these structures formed by stars, which obviously formed a lot earlier, only 300 million years after the Big Bang, then there's a problem. There's something we're not understanding about early star and galaxy formation. And then we have the early supermassive black holes. Now, this is a black hole called UHZ1. We have 2 images here. The one on the right is the JWST image, and that shows a little blob, but that's actually a galaxy that hosts the black hole in the image on the left. This is an X-ray image from the Chandra Space Telescope of the black hole itself. Now, this was in existence less than 470 million years after the Big Bang. So we had a supermassive black hole less than 470 million years after the Big Bang. This is a problem. So was it formed from stars collapsing into smaller black holes and then coalescing as we believe happens with at least some of the supermassive black holes? Or was there a giant cloud of molecular hydrogen that collapsed in on itself and under its own weight formed this black hole? We don't know. So more data is needed on that. But it does indicate that there's something we're not understanding about how we can have these supermassive black holes this early in the universe's history. And it does require revision of the early black hole formation models. And there's just a zoomed in image of that black hole in X-ray on the left and the host galaxy that it's at the center of in the JWST image, excuse me, on the right. Then we have the little red dot galaxies. Now, these are plentiful in the early universe. There are lots of them. 6 are shown here, and they're called little red dots because that's exactly what they look like. And what we now think these are young galaxies that have, again, supermassive black holes at their centers that are incredibly efficient at turning gas into stars. And they are compact, they're red, they're what we call AGNs. They have this active galactic nucleus, which is a feeding black hole at the center, feeding on material around it at an astonishing rate. And we've never seen this rate of black holes consuming material this early in the universe's history. And the AGN feedback is likely shaping these galaxies. Well, what do we mean by the AGN feedback? Well, basically what happens is that the wave of radiation, the intense radiation from these supermassive black holes feeding, spreads out through the galaxy. It dissipates gas in the galaxy, preventing the galaxy from forming more stars, acting, as you like, as a throttle on star formation in the galaxy. And these galaxies are likely being shaped by that sort of activity. But we don't know an awful lot about these little red dots as yet. But there are lots of them. I think the Webb has discovered, I think 60 or 70 of this type of galaxy in the very, very early universe. And again, all this poses problems. So to summarize what the JWST has found, unexpectedly mature galaxies less than 500 million years after the Big Bang, suggesting those galaxies formed and matured much earlier than the standard lambda CDM, the lambda cold dark matter model, predicts. So there's something probably wrong with our lambda CDM theory about the early universe and how fast stars and galaxies evolved. You've got high stellar masses and star formation rates. Some early galaxies exhibit stellar masses and star formation rates that exceed theoretical expectations for such young cosmic epochs, implying that these galaxies are much more efficient than forming stars than we had thought possible, or even perhaps that these stars are formed, or the early stars were formed in a way that we're not aware of, that there could be another mechanism for forming these stars that we're just not aware of. That would be absolutely incredible if that turned out to be the case. You've got compact high-density structures. Many of the earliest galaxies appear extremely compact and dense, challenging models of gradual hierarchical assembly via mergers and slow gas accretion. What does this mean? Well, the way generally that we think galaxies get to grow so big is by consuming smaller galaxies, as in the case of our own Milky Way galaxy. So galaxies come together to form bigger galaxies, which then get eaten by bigger galaxies in a sort of a hierarchy. And it could be that we've got this wrong, that there could be other mechanisms at play there that we're just not aware of. You've got irregular morphologies and dynamics. As you've seen, some of these early galaxies are sort of irregular, clumpy or disk-like structures. These are not at all how we expected them to be in terms of their shape and their morphology. There may be other mechanisms at play governing the shape and morphology of these galaxies that we're just not aware of at the moment. And also, of course, we shouldn't leave dark matter out of this. As you may know, most galaxies are surrounded by a halo of dark matter. And what we're seeing from the James Webb indicates that these halos formed much earlier than expected. We may need to revisit the model of dark matter behavior in the early universe as a result. So how do we fix all this? These are the problems with what the James Webb has shown us. What might be the fixes for solving these cosmic conundrums, if you like? Well, obviously, we need to revise our galaxy formation timelines. We may need to account for galaxy formation within 200 to 300 million years after the Big Bang, much earlier than our current models predict. And what this implies is a more rapid collapse of gas into dark matter halos and faster onset of star formation. So the dark matter halos may have formed much earlier, and the stars may have also formed much earlier and, form these galaxies. We may have to rethink our star formation efficiency. Models must incorporate much higher star formation efficiencies in early galaxies, suggesting that primordial gas cooled and condensed into stars more effectively than expected, possibly due to enhanced turbulence, different feedback processes, or altered initial mass functions. So there's a lot to think about with how we view the formation of these early stars. Our models of dark matter halos may be wrong. By the look of it, what it is suggesting is that our lambda CDM models may need refinement to permit the earlier emergence of more massive dark matter halos, potentially requiring modifications to small-scale structure growth rates or reconsideration of the whole warm versus cold dark matter scenarios. So that's another thing that needs looking at. Accelerate chemical enrichment mechanisms. Well, as I said earlier, some of these galaxies have got much heavier elements in them than should have existed at that time, because don't forget, heavier elements are created by successive generations of stars. And that implies that the population 3 stars, I know this is confusing, but the first generation of stars are actually called population 3 stars. They were supermassive stars. Perhaps they formed and died more rapidly than we think, or that these early galaxies experienced much more intense starburst activity and supernova-driven mixing of these gases and elements much earlier on than we thought. But we don't know what might be the mechanism for that. And we need to look at our models of galaxy growth. Once formed, how do galaxies grow? And what the James Webb is showing us is that there's much less chaotic growth than expected, that there is order appearing in the structure of those galaxies much earlier than we thought. And there we are. So we also need to incorporate non-standard initial conditions. May imply that initial density fluctuations, the one I talked about that you can see in the cosmic microwave background, were more pronounced or differently distributed than predicted by inflationary models. So even the inflationary model has to come under scrutiny to understand what the hell's going on here. And there we are. So to fix all of these problems needs looking at a lot of ideas that we thought were correct. As you can imagine, this is not going to be an easy task. Fixing all this is not going to be easy, because it means looking at a lot of things and a lot of scratching of heads, and a lot of new ideas need to come up to try and fix these problems, because it's painfully obvious, I think, and I think most astrophysicists and cosmologists would agree, that we have definitely got the early universe wrong, according to what the James Webb Space Telescope is actually seeing. So there you are. So that's just a trip through what the problems are and what the solutions might be. But it is going to be very difficult to fix all of these separate problems. Ian says, isn't time itself distorted at such distances speed, thus causing us to see the black hole much further away than it actually is, and therefore not as old as it appears? Not really, because what we use to establish the distance to these objects is their cosmological redshift, and that really doesn't lie. But there have been suggestions, Ian, that we have got the whole age of the universe wrong, that it is in fact much older than we believe. But there's no real evidence for that as yet. There's no real reason to doubt the Big Bang. There's no real reason to doubt the age of the universe, because that's pretty well established. So we would just have to wait and see. So there you are. Any comments, guys? Lou, have you got anything to say about that?
Yes. So Lane is, or is it Ian? I'm sorry.
Ian
is correct that general relativity works in the neighborhood of a black hole and affects the perceived distance and velocity of something approaching the event horizon. But you described it accurately, Andy, that it doesn't affect our actual distance measurements to the black hole.
No. Well, thanks for your question, Ian. So, you know,
if you want, Andy, I've actually got on it. You know, you were talking about supernovas. I've actually got, if you just bear with me a second, I've actually got here some images of, let me just flick through this. This is all past images of Webb, of the early galaxies. That's not the one. Jades, many supernova that exploded even further in the past. This is what this Jades was the one I was looking at. Now, if you look here, we've actually got the supernovas that you're talking about actually in view, and they've got them arrowed, so you can actually see that in 2022 where there was no, say, let's go from left to right. In the first image on 2022, there's, if you look where the arrow is on 2023, in 2022 there wasn't a spot. Again with 2023 on the bottom, again you've got one arrowed, and it's there's nothing there in the top one, and then in the third one, you can actually see that there's a small dot, but if you look on the bottom on 2023, it's gone. So it has been detecting these supernova, and as you can see, you've got your Z value at the top here. Now this is the redshift value that you were on about, and these all vary. Yeah, because I mean the highest we've seen is Z14, which is what you've shown, and there was one for Z13, which is 330,000. Yours was 300,000 years after the Big Bang. So we are seeing further and further back. So yeah, let me just come back to the studio.
Absolutely.
So, yeah. So we are detecting these supernova further back than we thought we would, and James Webb's been absolutely wonderful at this.
Absolutely.
So,
absolutely.
Oh, that makes sense. Anyway, sorry.
Thanks for that. Yeah, I mean, and Morgan makes a point. Let me put this up here. Hi, Morgan. Yeah, a galaxy becomes a fossil. Yeah, I mean, we are looking at fossils from the early universe. We are like, or not we, cosmologists, I should say, are like archaeologists or paleontologists looking back to an era where there's very, very little evidence left of what actually happens. And we have to sort through that evidence to find out. But you're totally right. I mean, it's exactly like dating fossils. Exactly so. So thank you for that. Okay.
I mean, there was one image that I thought was really fascinating, if I can just go back to this again. And it was the lensed galaxy that we just flicked through, and it's this one here. Now, this galaxy in the middle is actually lensed, and it's lensed, and in some places it's actually been magnified. The brightness in that has been magnified up to 40 times. But
Right.
what they've made, they found fascinating is about this, is you can see all these individual globular clusters actually in the galaxy itself. I don't know if you can see my cursor, but there's absolutely, you can see there's a ring of globular clusters, but this looks like this because it's an actual lensed, it's something in the foreground has actually bent the light, and it's actually beyond the object in the foreground has gone. But also it's interacting. There you can see there's two companions, and they believe that these two companions are interacting with this galaxy. They're actually orbiting each other as well. And of course, every time they have an interaction, it squeezes the gas that's actually in the galaxy, because this has been found to be very hydrogen rich, which of course we would expect because it's such an early galaxy. And of course, once it compresses the gas, you get more and more gas formation. And the different colors of this necklace of sort of like clusters are actual different ages. So this is a galaxy that's actually forming at the, going back. I can't remember what this one was. That's not the one. If I can just come back one more, it might tell me how far away it is. Because there was a bit of quite a rise up. See, it says magnified 40 times, which gives us the different colors. The first time was identified a forming galaxy.
So it existed about 600 million years after.
600 million years after the Big Bang. So this is quite an old galaxy, and it's, of course, the light's just reaching us now, but you can see it was actually forming when the light actually left that galaxy. So I find that absolutely fascinating, that we can actually see the individual building bricks of a galaxy,
and especially the globular clusters. I mean, that's as gravitational lensing goes, that's quite a coup, I think.
Yeah, it is. It's very good. And like I said, and also to realize that these two companions as well are interacting with it. It's good.
Amazing.
Yeah,
Okay, then.
amazing.
So that's the situation with the Webb telescope. But please don't pay any attention to people, especially on social media, saying that everything the James Webb discovers proves the Big Bang doesn't happen, because there have been lots of people saying that. There haven't been any, as far as I'm aware, any media stories saying this. So this is people not understanding something and coming to completely the wrong conclusions. Like that's never happened before. So anyway, that's the James Webb situation. What Lou's going to talk about now, though, is another big problem, a big problem, capital letters, big problem, with the Hubble tension. So, Lou, if you're ready, I'll just put that up for you. So tell us what this is all about then, Lou.
Yeah, thank you, Andy, and a brilliant presentation today. And it just so happens, we put these together separately, but just so happens that it leads very nicely into what I'm going to talk about.
Oh, well, thank you, Lou. It was fun to do.
And what I'm going to talk about is a little bit heady. So listen, $20 or 20 pounds to anyone who can stay awake through this, and just send a self-addressed stamped envelope to Andy, and he will pay you.
Right. Absolutely.
Right. Just to be clear on that. All right. So as Andy is pointing out, there are still some problems, some things we don't know in the universe, which keeps us astronomers employed. So that's good news. So let's start back around 1924, where Edwin Hubble was observing the Andromeda Galaxy. And he knew, thanks to Henrietta Leavitt, that there were things called Cepheid variables, whose rate of blinking on and off was related to their absolute brightness. So he had a way of gauging a distance to the Andromeda Galaxy. And I think he underestimated the distance, but it was very, very large. The actual number is 2.5 million light years. But it was far enough, by the way, this is just a separate comment, that when he showed Shapley his data, Shapley, who had been arguing that there are no other galaxies, Shapley immediately conceded and said, yes, that Curtis was correct, and there are other island universes in the world. So here we have a distance using Cepheid variables to have that period luminosity relationship, period of pulsation to their distance, to their brightness, to gauge the distance to the Andromeda galaxy. That was a big finding. And so, like any good astronomer, he made a graph.
Well, hey.
And here it is. He plotted the distance using the Cepheid variable measurements to various galaxies. And he knew their recession velocities by measuring their Doppler shift of I think, mostly hydrogen lines, individual hydrogen lines in their spectra. So he had a distance, he had a velocity, and he plotted it up. And look at this. It's they all fall pretty closely around a straight line. The importance of this line is that its slope, right, y over x, its slope is the Hubble constant. And the units of the Hubble constant, which we write as h naught, are 1 over time. And that time is the age of the universe. So the Hubble constant is very important. And this graph, by the way, also uses type 1a supernovas for more distant galaxies, which are another, what we call standard candle objects that we know exactly what their brightness is. So when we see how dim they look in galaxies, we say, aha, I know how far away that galaxy is. So this value for the Hubble constant, this y over x on that graph, velocity over distance, has been thrown around for a while. And it's converging to not one value, but perhaps a set of values. And here you can see how the value, or the accepted value for the Hubble constant, has been changing over time. And so, again, that this important constant in astronomy tells us what the age of the universe is. So let's just move on a little bit. And let's talk for a moment about another way to gauge the age of the universe. Okay, the way we just looked at was looking at very specialized stars in galaxies far, far away, as they say, and knowing the brightness of those stars, and then we can see how dim they appear, and we get a distance to galaxies, and we see that the universe is expanding at a certain rate, and that is the Hubble constant. But there's another way to derive the Hubble constant, and that is by looking at the leftover energy, I guess I'll say, from the Big Bang, the cosmic microwave background radiation. This is the radiation that was released shortly, in cosmological terms, after the Big Bang. And as the universe has expanded, this radiation has cooled, and it exists now everywhere you look at a fairly, but not precisely, constant temperature of about 2.725 degrees Kelvin. This is a plot of the black body spectrum of that temperature of the microwave background. And you can see the data points here fall very nicely along a 2.725 degree Kelvin black body curve. Very, very nicely. So, the cosmic microwave background, it fills the entire universe. It's the leftover radiation from the Big Bang. And when the universe was born, nearly 14 billion years ago, the universe was filled with a very hot plasma. And as Andy, I think, has already alluded to, during the first 380,000 years of the universe's existence, the light from photons in that universe could not escape because it kept running into electrons. Atoms, it was too hot for atoms to form. There were free electrons everywhere. The path length that a photon would take before it crashed into a scattering electron was very short. This process, by the way, is called Compton scattering. And so it was like a wall was there that light could not get out. But at about 380,000 years, the universe had expanded enough and cooled enough that atoms could form. And at that point, the light from what we now see as the cosmic microwave background could emit into the rest of the universe. So we've been measuring this interesting radiation with a number of spacecraft, most recently the Planck satellite, and it measured the CMB temperature, as I was saying, to 2.725 degrees, which is about 270 degrees below 0 Celsius. Pretty cold, almost everywhere in the sky. But almost is the most important factor here, because there are tiny fluctuations in that temperature by just a tiny fraction of a degree. They represent distances in densities of structure on both small and large scales that were present right after the universe formed. So you might imagine these as seeds from where galaxies would eventually grow. Planck's detectors are so sensitive that temperature variations of just a few millionths of a degree can be measured. And so this provides a lot of insight into the density fluctuations of the early universe. Now, the map that you see here, that I have strategically not commented on until now, is the data that Planck took, the temperature of the universe in all directions that the Planck satellite measured. The blue areas represent slightly colder, slightly denser regions, and the red spots, the red areas, represent slightly hotter, slightly less dense regions. So the temperature differences on this map are only about typically 0.0002 degrees Kelvin. Right? So we said the cosmic microwave background radiation was very consistent across the universe. It is, but there are tiny temperature fluctuations. The age of the universe, then, can be derived from the CMB, cosmic microwave background, we call it the CMB, by measuring its temperature fluctuations, which provide information about the early universe's composition and expansion rate. This information is then used in conjunction with cosmological models such as Andy referred to, the lambda CDM or lambda cold dark matter model to calculate the time since the Big Bang. In addition, the CMB has a redshift, right? It's light, it's electromagnetic radiation. It's been propagating through the universe. As the universe expands, it has a redshift. And I could hardly believe my eyes when I saw this. The redshift value, the what we call Z, Andy showed you a redshift value, I think of 14 earlier, or maybe that was Daz, I forget.
No, it was me. Z for the CMB is 1,089, which gives you a velocity of 3.27 times 10 to the 8th meters per second. Now, our wise audience will say that's faster than the speed of light, and it is. But when you take into account general relativity and a few other factors, that lowers that redshift a bit to actually, on average, under the speed of light. And all of this indicates that the universe was about 380,000 years old, which is that point in time, that 380,000 years is called the epoch of recombination. And that's when the CMB photons ceased to be scattered by free electrons. Atoms could form and light could get out. So
you can combine this redshift with cosmological models, such as lambda CDM model, and the Hubble constant, and use this to estimate the age of the universe at the time of CMB formation. And then you extrapolate back to the beginning of the Big Bang. It's a little, I mean, if I were to show you the math, Andy would be sending out lots of 20-pound notes. So I'm not going to do that. And however, I think I may, I'm going to talk about the next plot here just briefly. I have a few of these graphics, and I don't want to go into them tonight, but I will just say in general, this is called the cosmic microwave background power spectrum, and it measures, or it reflects, the temperature differences on the y-axis with the size of the areas of those temperature differences on the x-axis. And all I'm going to tell you tonight is that the structure of this graph, of this power spectrum, tells us whether the universe is flat with the first peak, how much total matter, baryonic plus dark matter, there is in the universe with the second peak, and how much dark matter there is, if you believe in dark matter, in the third peak. So it gets a little involved and not quite important enough for this talk, but we will get back to this because this is a very, very important and eventful graphic. So we'll get back to that. So let me just skip through a few slides here. I just don't think we want to go here today. Okay, there we go. Now I feel better. Thanks, guys. All right. So we have at least two methods of deriving the Hubble constant and therefore the age of the universe. One is by looking at the standard candles, these stars, which tell us how far away galaxies are. And the other is using the remnant energy of the Big Bang, the cosmic microwave background. And it turns out that these two methods produce very different values. So that, when Andy said, there's a problem in, what did he say, in River City? There's a problem. The Hubble constant that we get from each of these methods is different. What you're seeing here in this graphic on the screen is kind of a graphic of the whole life cycle of the universe from the Big Bang with quantum fluctuations to faster than light inflation era, to dark ages where light could not emit, to the first stars forming and so on. So it's just kind of a neat graphic. And somebody stuck the WMAP spacecraft in there, the Wilkinson Microwave Anisotropy Probe. Okay, anisotropy, not same temperature. So that was one of the previous spacecraft that measured this CMB. All right, back to the story. Let's see. So two methods of measuring distance: lambda cold dark matter and galaxies. When we use the lambda cold dark matter and the CMB, cosmic microwave background radiation, we get a result of H0, which is the Hubble constant of the rate of expansion of the universe now, called H0, of about 67.4 plus or minus roughly 0.5. More traditional techniques, observing the supernovas and Cepheid variables, we can get from both the James Webb Space Telescope and the Hubble telescope. And they give you a number not 67.4, but something like 73.24. Clearly, for the Hubble constant, clearly these two values are not in agreement. Here's a way of looking at it. Here in blue, you see values for the Hubble constant over time using Cepheid variables. In red, using red giant branch stars, that's another technique that can be used. And in gray here, you see the value for the Hubble constant derived from the cosmic microwave background. So just another way of saying we have a problem. There we go. Many methods have been used and many studies have been initiated to try to force these two models together. So far, they have met with no success. The top 2/3 of this table here represent various research studies into the Hubble constant, the age of the universe, and the value for h naught from looking at galactic distances. The bottom 6 represent derivations of the Hubble constant using the CMB. So once again, you see they're not at all in line. I just can't go a presentation without some math. I'm sorry. Andy's going to be sending out more letters and more letters. Here's how you do it with the Hubble constant. Slope of the line is y over x, which is velocity over distance. Velocity has units of distance per time. Distance, of course, has units of distance. And if you put distance per time over distance, you get 1 over t, and that t is the age of the universe. Turns out in seconds, so you have to do a little magic with that number. So 1 over h naught is the age of the universe. If you use the 67.4 or 0.5 number to derive the age of the universe, you get a universe that's about 13.8 billion years old. If, however, you use the figure of 73 for the Hubble constant, you get a universe that's a bit younger than that, and that's how the math is done. So we need to resolve this. Okay, so it was thought perhaps we don't truly understand Cepheid variables. Maybe the observations of Cepheids with, say, the Hubble Space Telescope are being combined with other stars in the region, and so we don't actually get a true picture of the Cepheids on their own. So a new study using just JWST observations has recently been released. And one of the advantages, by the way, of the James Webb over Hubble is that Webb observes Cepheids in infrared light, which penetrates interstellar dust much easier. So the Webb observations are also better at addressing this issue of crowding, right? That we're in our field of view, we have a Cepheid variable and we have other stars because it has better spatial resolution. So it looked at this. It looked at this issue of Cepheid, what's called Cepheid overcrowding, and the results indicate that this is not a problem. With that Hubble, it was actually accurately representing the brightnesses and therefore the derived distances to these galaxies with Cepheid variables in them, and that was not the problem. So we're still stuck. This is just a graphic showing the Hubble measurements in white and the James Webb measurements in red. And so, yeah, the James Webb measurements have less scatter in them, right? Have better resolution, but the average of both of these series is essentially the same. So that's not the problem. So now as astronomers do, we get into the area of, well, now what do we do? Let's make stuff up. That's what we're left with. So we can, there are a few possible theories that might resolve these this difference. One is that what if we live in a low density bubble in the universe? If you use computer models and you make the density of the region around us roughly half the density of the bulk universe, and I think if you kind of place us closer to the edge of that bubble, then the higher density matter outside the bubble would be tugging on galaxies within the bubble, giving them a higher recession velocity than would be expected. So perhaps that's a way of adjusting the observations of type 1a supernovas and Cepheid variables in galaxies. So you say we leave the CMB alone, that works well. Let's focus on the distance ladder from standard candles. Another possibility is, well, okay, so we don't know what dark energy is. We just gave a name to something. Well, now there's early dark energy, believe it or not. And this would be similar to dark energy, which drives the expansion of the universe today. But this early dark energy would come into existence and then would disappear. All right. So in other words, a special shove, so to speak, in the very early universe. And then this EDE, this early dark energy, replicates the formation of more large, bright galaxies in the universe, which is consistent with the James Webb's observations. So this actually solves two problems. One, the Hubble tension, the difference in the two values that we derive for the Hubble constant. And two, the fact that we see more large, well-formed, bright galaxies in the early universe. So that's rather interesting. Another possibility could be that we have not calibrated the brightnesses of type 1a supernovas correctly. Now, we use type 1as for more distant galaxies. You can use Cepheids for galaxies that are somewhat closer, but after a while, Cepheids are not bright enough when we use type 1as for the most distant galaxies. So, so they may need recalibration. This can be done by observing them in galaxies alongside Cepheid variables. So this would be a kind of intermediate distance where we'd see both of these, and we'd kind of calibrate the type 1a supernovas against the Cepheid variables, which we think we know fairly well. And then, as I mentioned earlier, we could also use what are called TRGBs, the tip of the red giant branch. This is for the, what's the graph I'm talking about? Andy, I'm blocking.
Well, the Hertzsprung-Russell.
Thank you. Thank you. The Hertzsprung-Russell diagram. These red giant stars, we can know their brightness fairly accurately, and so we can use those as calibration sources as well, and some other things. But the bottom line is we don't know why there's a difference. We don't know if we should adjust our distance ladder from the observation of galaxies or from the cosmic microwave background. We don't know how this would affect the models that we have of the formation of the universe. So it's a big puzzle right now, which is so exciting. But there's no solution as yet. And so stay tuned. Perhaps next week, somebody will find the answer.
Indeed so. Indeed so. Thank you very much for that, Lou. That was absolutely great. I don't want to put you on the spot, Lou, but do you have a gut feeling as to what's wrong?
I like is the wrong word. This second possible solution, this early dark energy, solves both problems of the Hubble constant differences and the observations that James Webb is making of galaxy formations much earlier in the universe than we thought possible. So that's very intriguing.
It is. It is. Because when you think that we believe that inflation was some sort of a phase change in the universe. And then if dark energy came along, what did you say, just a few thousand years after the Big Bang, then, you know, that is doubly intriguing, because, you know, obviously something happened to allow dark energy to overcome gravity and start accelerating the expansion again.
Right.
But to me, I mean, not that I'm an expert or anything, but to me that makes more sense that would have occurred in the early universe than billions of years after the Big Bang.
It does, but we don't. Here's what's missing. These are cool ideas, somewhat fanciful, but maybe one or both of them, or many of them are right. But we don't have a physical mechanism.
No.
For example, why dark energy to begin with, but why early dark energy? What is the physical mechanism that would make the universe expand even more quickly during the very early universe and then dissipate? We don't know. You need a physical mechanism to really hang your hat on these. And I think that's
and again, it's like inflation, isn't it? We don't know why it started and we don't know why it stopped. So, and we don't know the mechanism. So, yeah.
Right. And why are they all why are they called apartments if they're all stuck together? I mean, these things need solutions.
Yes, indeed.
And we don't know the answers.
Yeah, absolutely. Yes, indeed. But this is what astronomy is. This is why it's so exciting. It would be really boring if the James Webb had just confirmed what we thought we already knew, that the cosmic microwave background had confirmed what we thought we knew. Astronomy is constantly changing, and it will always be thus. And I think we're very lucky to be alive at a time when we are addressing or beginning to address these fundamental questions. If you think back, you know, I can remember when I was a child, and you know, there weren't really that many big, enormous puzzles like this, because we thought we had everything. Well, not everything, but a lot of things worked out. And the textbooks on astronomy really didn't change very much. But
when you were a child, the sun was orbiting the Earth and everything was very simple. So.
Yeah, absolutely. Yeah, absolutely. Well, when I was a child, the Earth had only just formed, of course. So there we are.
It was still hot, wasn't it? Still hot to walk on.
Absolutely. So these are all big questions, and you know, answers may come along just completely out of the blue through something completely unrelated, which is what often happens. We solve these things by serendipitous discoveries that can you know, that we didn't think were important at the time,
and new technologies.
And new technology.
They produce quantum leaps in our understanding, just like James Webb and Hubble
and of course LIGO, which has completely revolutionized our view of the universe. It's completely demonstrated relativity to be correct to the nth degree yet again, but it's opened a completely new window on the universe. Because from the beginning of astronomy, going back thousands of years, the only thing we'd had to examine the universe through was light. And now we can do it through the observation of gravitational waves, the very structure, if you like, for space-time itself.
Which were not affected by Compton scattering.
No, exactly so. Exactly.
Right? So that wall, that 308,000 year wall is not there, I think, for...
No, it isn't.
Andy?
It isn't. No, it isn't.
Waves.
Theoretically, LISA, the European Space Laser Interferometer, being launched at the moment, I think it's 2034, but I did read somewhere that they may bring it forward because the preparations are going so well. That may be able to detect these primordial gravitational waves from the Big Bang itself, which are not constricted by that opaque fog at 380,000 years, because light couldn't escape the early universe, but gravitational waves could, because they are space itself, not something in space. So exciting times ahead, very, very exciting times ahead. And when Einstein is built, it will give us a gravitational wave detector, which they're saying could be up to 20 times more sensitive than LIGO. And there are new gravitational waves planned. They've started the one in India. China say they are building 3 gravitational wave interferometers. And the whole field is just opening up rapidly. And it's a very exciting time to be alive, in my opinion. Having said that, of course, we're now going to look at people who try to spoil our understanding of the universe and prove that we may understand these things, but there are a huge number of people who just really don't have a clue about the universe in any way, shape, or form whatsoever. Before we get on to Einstein of the Week, can I just ask you, if you want to support Space Oddities, you could be so kind as to buy us a coffee. You can scan this QR code or click the link that's just appeared in the chat, and that will take you to our page at Buy Us a Coffee, and you can make us a small donation of a coffee as a present. All money we ever receive from you viewers goes towards keeping Space Oddities going, and we've managed to do so for 3 years now with your help and support, and we are very, very grateful to all of you who have given us donations, because it is very kind of you. We obviously appreciate how tough money is for everybody these days, and for you to spend any money on Space Oddities, it's really thrilling, and we're very, very honored to receive your donations. You can, of course, help us in other ways. You can go to the Space Oddities shop and you can buy your lovely Space Oddities merchandise in the form of t-shirts and hoodies. Of course, summer's here, so you need to go about wearing a t-shirt. And what better t-shirt to parade around your block than the wonderful Space Oddities t-shirts, and get yourself a hoodie for the autumn as well. So so go and have a look at those. Very reasonably priced and very good quality. And again, we thank you for your support. That's all we can say. All right then. So if you're new here, you may not know that each week we take a dive. We put on our scuba outfits and we delve into the sewage of social media for a look at the ways in which people just don't understand what's going on in the universe, even on a very, very basic level. And we always have a laugh at this. And I know we shouldn't laugh at people, but why the hell not? They're stupid. So
we're going to get a few letters. Okay.
So anyway, let's have a look at Einstein of the week. Let me just bring this up. I think we got 6 or 7 this week for you to have a look at. So this is Einstein of the week, and I hope you can see that. So first Einstein of the week, guys. First of all, it's a little quiz for you. What is that an image of?
That's isn't that 67p?
P67, is it?
Yeah.
67p, and what's underneath it?
London.
No.
New York City?
No. That's an unfair question. Come here. It's actually Los Angeles. So this is an image showing you the size of Comet 67p in relation to Los Angeles. Somebody completely misunderstood this and said, wow, the media isn't even covering this.
Lou falling off his chair.
Oh, God.
Yeah. So there we are. They're so focused on the tornadoes, they've neglected to cover the comet dropping on Los Angeles.
Oh.
And well, the tornadoes create a bigger disaster, don't they?
Of course. So anyway,
I can't believe that.
There we are. Moving on. This is only number 6, by the way. Coming in at number 5. This is an image showing how far the Voyager spacecraft will travel in 1 million years. And I don't know whether you can see it. There's a red line there representing how far across our galaxy Voyager will travel in 1 million years. Yeah?
Yep.
Yeah. Okay. Right. Are you ready for this? That image is just not true. Man has never invented a spaceship that could travel so fast to capture such an image.
Oh,
Oh dear.
I know. Yeah.
Brilliant.
But this is in the aliens atlas, not ours.
Yeah. Of course.
Yeah,
Oh,
their atlas of galaxies.
Yeah.
so they're smart enough to know that the galaxy is large enough that in order to get an image like this, you'd have to be very, very far away from it.
Yeah.
They're not smart enough so that is impossible, but they're not smart enough to know that this is just a graphic.
Yeah.
Well, either a graphic image or maybe an image of another galaxy.
Yeah. Yeah. And they're also not smart enough to realize that the galaxy doesn't have lines.
Yeah, or actually labels.
Well, now how do you know this, Andy?
that's prompted Paul to send us $10.
Has it? Thank you, Paul. Thank you very much. Oh, let's see if we can get some more out of people. Right. Okay. Current solar activity, as you may know, there was an X2.7, I think, flare released last week that disrupted radio communication across the Earth. Well, not all of it, obviously. And there were a lot of comments on social media about this solar activity. This flare activity seems to have an 11-year-old cycle.
What?
The penny drops.
Hey.
Yeah. Yes.
Oh dear me. Yeah.
Trying to work out that the sun, yes, does have an 11-year cycle.
Yeah.
So there you are.
Well, at least the penny finally dropped.
Yeah, at least the penny finally dropped. True.
Yeah, it rolled around the rim for so long, but it finally did.
11 years, in fact.
11. And to be fair, I did reply to him and just tell him a little bit about the solar cycle. So there you go. Stop launching rockets, coming in at number 3. The research and studies of some scientists is wrong. Stop wasting the air of the Earth by means of rocket launches or outer space explorations. The air of the Earth is thrown into the outer space. Please stop wasting the air of the Earth. Thank you.
Huh.
No one is.
No.
Where do they,
Okay,
how do
then.
they figure that out?
Yeah. So we're punching holes in the atmosphere and the air.
So let's
It's rushing out.
Yeah.
Well, I don't want to be. There are other ways of wasting air.
Yeah.
Yeah.
But,
And they definitely are.
Yeah.
Okay. Coming in at number 2 this week. More religious lunacy. So this is a picture of 2 of Saturn's moons, Titan and I think it's Theia. But anyway, so the comment about this, here we go. Welcome to the video. Blessed are your eyes because they see promised ionated Jesus walk foretold Egypt, automatic prophet like August, heavenly sent ahead of his kingdom of the light and immortal 3D one eternal life, reloading the moon for the night, yet drivers NASA.
What?
End of war, burn all funeral covers, Babylon, God turn.
Well, finally one that makes sense.
Yeah.
You know.
He's got his finger on the pulse.
Yeah, absolutely.
Huh.
Has he used enough emojis there?
Yeah.
Reloading the moon. For the
Reloading
night.
the moon.
That's so
Yeah.
poetic.
Moon.
Yeah, I know. Anyway, Einstein of the week this week was also about the solar activity. Are you ready for this one?
No.
Don't solar flares cause plagues or something?
Oh,
Okay.
I wonder if they're confusing plagues with plages.
Oh, no, I doubt that very much.
I don't know.
I doubt that very much.
Well, just tell her yes. Remy, right.
Yeah, don't worry, I did. I said it causes plagues and all sorts of other nasty things.
Well, the last one caused COVID.
Oh yes,
So could be.
Aren't we selling some SpaceOddities insurance for those things?
Yeah, quite cheap as well, quite reasonable.
Yeah, very cheap.
Yeah.
Very good deal.
Yeah.
Okay, so there we are. So that's Einstein of the week for this week. More next week, undoubtedly. So there we are. So yes, so there was a lot of coverage in the media of the radio blackouts because of the X 2.7 flare. But as we always point out, X 2.7 is not actually that enormous a flare. It's in the biggest class of flares, the X flares, not the X-men, the X flares, and like DASWERs. And it's but as an X flare, it wasn't that big, but it did cause radio disruption. But the funny thing was, on social media, people were saying, "Oh, my TV went off for half an hour, and you know, my dishwasher stopped working, and all these things." So there you are. It's a strange old world, isn't it? It really
It certainly is. Yeah.
So there we are. Of course, you know, we're at solar peak, so these things are to be expected, and you know, there's probably going to be a lot of solar activity yet to come before it starts really dying.
Oh yeah, there's lots more to come. Because I mean, if you don't mind, let me just try something. I did have NOAA running. Oh yeah, it's still there. Let me just see if I can share the NOAA page. NOAA.
While you're doing that, reading an article yesterday saying, "Are we prepared for the next major solar catastrophe?" And
No, we're not.
No, and we can't be prepared because there's very little you could do to prepare
That's
for
right,
it.
yeah.
So
Yeah, because I mean, at the most, I mean, as regards the radio blackouts, they happen within 8 minutes of any flares, and they can last either a very short while, or they can last a long while. But if you just sort of a longish while, but of course they start with the lower frequencies, and then the higher the flare. Now, this is what I was just going to show you as regards blackouts. I don't know what's this covering. This is covering. Is there a scale on here? Something. It says here valid at.
Well, underneath
What I'll do is I'll just play it. And then you'll be able to see. Now, if a flare happens, see the purple area. That is the day side.
right.
Okay, so that is what is happening at the moment. Now, what we're looking for is, I'll see if I can make it big as well. Now, if we watch it, you'll see it slowly moving towards the left, and you can see the colors are changing. Now, there's a flare, a small one,
Wow.
where it actually changed to blue. When you actually get large ones, they will come all the way up to the red. And there are images you can get which is plotted all the radio pathways, and you will actually see that when you get a big flare, they will totally disappear. So there is no communication being able to
Wow.
happen there at all. So of course, but I don't think there's a big one. We've had a big one for a couple of days, but you can see it changing color and intensity. That is the magnetic energy interfering with coming from the sun, actually interfering with the radio. That wasn't a very good one. But also you can see these little side bars actually moving backwards and forwards. But also we were talking about the actual cycle. If I come down further, now this is on the NOAA site, and you can find a lot of information. Well, here's our sunspot cycle. Now you can see we've started to decline now, but as we said, the actual the sun has become quite very, very active, but in a different way to what we had about sort of like 3 or 4 months ago, where we had lots of active regions. But now we've actually got it's on the decline. You can see the sunspots are declining, and so we will it eventually will actually disappear.
Yeah.
Let me see if I can just get rid of this for you.
There is not infrequently a double peak in the cycle.
Yeah.
So we don't know if that's going to happen.
If you look along the bottom here, you can see all the previous cycles, and you can see they've got sort of like a volcano shape along them, and that's what Lou is referring to. They will drop down. We will reach a peak, then it'll start to drop, and then we'll peak again. And as you can see, it's up and down. And if you just put your cursor on the thing, it'll give you the values for each month. So they are varying. And then, of course, when we were up here, the monthly value was average was smooth value is 156.8 sunspots over that month, and that's when we reached the peak. But you can see they all do vary, and things like that. So,
Right. Thank you.
Well, I'm stuck.
Okay.
Can you get rid of that, Andy?
Yeah, I certainly can.
That's it. I've got it now.
Okay.
Right,
So thanks very much for that. That's very interesting. Yeah. So, you know, there's a lot of activity still to come. And, you know, there's very little as a civilization, there's very little that we could do to prepare for a big event that would have devastating effects on electronics, power grids, satellites, the lot. We just have to take it, basically.
Because we have had some aurora quite a lot over the last couple of weeks. We were getting lots of warnings because the sun is very, very active still, but for different reasons to what it was a few months ago. I mean, if you want, I can play you a video. Let's see if I can find it. Window. Screen. No, I can't. It's on there.
Okay.
But I'll sort something out, and then I'll actually show you. And it's basically from the 1st of this month to yesterday, and you can see all the action that's going on. So I'll see if I can sort it out for you while you're chatting on the next part.
Okay. Well, that's actually come to an end for today, apart from Michael. And Michael is going to now give us the constellation of the week.
Hopefully. Just bear with me.
Yeah.
Just hold on a second.
Certainly.
You got that?
Yeah.
It's actually got constellation of the week this time
instead of constellation of the month. Can you make it any bigger, Michael?
I can't actually. Just bear with me. Let me try something else. I will do that one, and then just bear with me. Then I'll do. What am I doing?
Okay. Well, not to worry.
Screen.
Not.
Change. Right. Let me just share screen again.
Okay. All right. So we do like to bring you a constellation of the week, viewers. Tell you a little bit about different constellations that you.
How's that then?
That's there. Yeah.
Yeah. That better. Okay. Right.
Hang on 1 second. We've got a scene up on the screen.
Right.
Okay.
Sorry, that was my bad. I was trying to load a video. Sorry, I do apologize.
Yeah.
Right.
Okay, Michael, off you go then.
Okay. This week's constellation of the week is Hercules. It's coming into the night skies at the start of the summer. So it'll be visible in the forthcoming months. It's bounded by Lyra in the east and Bootes and Corona Borealis in the west. And it's quite a faint constellation, but it's well worth looking out for in the summer, in the early summer nights. This is an outline of the constellation itself. There's no stars above magnitude 3, I believe, and just over 3. And there's 4 main stars there. These 4 stars here form what they call an asterism, which is known as the keystone in Hercules. So if you hear people talk about the keystone, that's where it is. And that's another diagram of the keystone. Okay, this is an ancient drawing of Hercules and Corona Borealis. how ancients saw what was being marked out in the sky by the stars. Okay, bright stars, as I say, not too bright. And again, with this constellation, Alpha is not actually the brightest. Alpha Hercules, or Razelgethi, don't know how to pronounce that, is magnitude 3.8, and there's just to the bottom left of the constellation. And Beta Hercules Corniforus is to the right of the constellation as you look at it in the sky. Okay, for Northern Hemisphere viewers, of course. Then Gamma Hercules is near Beta. That is magnitude 3.74. And Delta Hercules, on the opposite side again, also known as Sarin, is magnitude 3.12. Okay, deep sky objects. Deep sky objects there's two main ones really. A lot of you would know M13, globular cluster, and but a much fainter constellation is M92 to the northern part of the constellation. And I've got a couple of images to show what they look like here. So that's the M13, and that's M92. This is M13, and that was actually this photo was taken by Roger. So
Roger who?
Roger Hyman.
Oh, right, that one. Right, okay.
That one. So I thought I'd take your image, Roger, and feature it tonight. Okay.
Charge him, Roger. Charge him.
Yeah. So that's a very nice view of M13. It's very good, very nice in small.
Yeah, nice one, Roger.
Yeah, a nice view of that globular cluster. And the next one is M92, and this is a Hubble Space Telescope view of M92. Quite a very populated by the look of it, but a lot fainter apparently than M13. There is a number of planetary systems within the boundaries of Hercules. I think there's about more than 15 planetary systems being discovered. The main one is 40 around the star 14 Hercules, and there's we know 2 planets orbiting that star, 14 Hercules B and 14 Hercules C. And as you can see, C is much further out than Hercules B. And that's just a diagram of how the planets were discovered. And I've forgotten the type of observation that found them. Sorry about that. Okay, so that's a quick view of Hercules. So.
Thank you very much, Michael.
Okay.
Right. Indeed. So there we are. So not a lot of deep sky objects in Hercules.
No, it's quite bland in that respect, really.
Yeah. Yeah. All right then. Well, we're going to. Daz, did you find your video?
I've got it here, but I can't seem to share it for some reason.
Oh, okay. Well, perhaps next week we can have a look at it then.
Yeah.
Okay. So
no problem.
We're going to wrap things up for this evening. Thank you so much for being with us on this Tuesday evening. We do appreciate the time you spend with us, as always. And don't forget, next week is our 3rd anniversary. So we will be doing something special for that, but we're not quite decided what we're going to do yet. If you have any ideas, then there's something you'd like to see for our 3rd anniversary, then you can always email us at info@spaceoddities.space. Always lovely to hear from you. So please do. Next week, apart from that, we'll be having some more stuff. There'll be more news, more Einstein of the week, and I'm sure another constellation of the week. So do make sure you join us same time next Tuesday at 8 p.m. UK time on the Space Oddities channel. And we'd like to thank you very much for being here. So from myself, from Michael, from Roger, from Daz, and from Lou, Have a lovely week. Hope the weather stays good for you.
Andy, I've just got it. So would you?
Let's do it next
Would you
week.
like to show it next week? Okay, then, mate.
Yeah,
No
do it
problem.
next week. Okay, so from all of us at Space Oddities, thank you for being here and a very good evening to you.